All right. So good afternoon. I hope y'all are having a good day so far. I hope this week's gone all right for you. I know the schedule this week's kind of wonky with CASP testing and everything. But you know, classes are really short. Days go fast. It's not too bad. So, welcome back. Today, the focus of class is going to be kind of like a review. I wanted to take an opportunity before we do even more new content to do a quick review of kind of all the main things that we've covered so far in the course. And I believe this has been, we've gone through the chapters in the same order on all the school sites, or at least close enough. So I'm going to start at the beginning and kind of review relatively quickly. It's going to come fast and it's going to be like drinking out of a fire hose. However, this will be recorded, and also the presentation that I'm using for today that's a PowerPoint is already uploaded into Canvas for you. So you will have access to it and you'll be able to look through it at a more leisurely pace if you like. Chances are we will not get through all of the review that's on this PowerPoint presentation due to time restrictions, as today's class is only 45 minutes long at most, right? That's the whole class period for today. So I'm going to share my screen and we will get going. This is what I want to do. Alrighty, so you should be able to see my screen now. This will be a review of all the chapters we've seen so far. And again, this is going to go kind of quick. If you do have any questions, you would like some clarification on anything that I'm talking about here during the presentation, please stop me and let me know. If you need more information than is provided on these slides, I encourage you to look back at the previous content in the textbook that goes along with that chapter, or within your Canvas course, having to do with that particular chapter or section. All right. Or you could even come to office hours on Mondays and ask questions if you need more detail than will be provided today. All right. So here we go, a time to review what we've seen so far. So main topics, things we've covered, right? We started in chapter 4, at least we did here at Orange Glen High School. I believe the other school sites did as well. Sampling and surveys and experiments. We moved on to chapter 1, how to describe and display categorical and quantitative data. Chapter 2, percentiles, mean, median, range, IQR, standard deviation, density curves, and the normal distribution. Chapter 5 is when we started dealing with probability and actually doing some calculations. Right. Simulations, conditional probability, and independence. In chapter 6, we talked about discrete and continuous random variables. This is where we began second semester. Transforming and combining random variables, binomial random variables, and geometric random variables. Then we moved into chapter 7, which has to do with sampling distributions of sample proportions and sample means. Then chapter 8 was confidence intervals for estimating population proportions and population means. Chapter 9 was our significance test for testing claims about population proportions and population means. And lastly, the chapter we just finished was chapter 10, comparing two populations or groups through confidence intervals and significance tests. These are the things that we have seen so far. It's quite a bit. So starting in chapter 4 was designing studies. We have sampling and surveys. We need to learn how to sample. We can use convenience samples or voluntary response samples, but those usually result in a bias, some form of bias. What's better to do is a random sampling, which we can do as a simple random sample, which we refer to as an SRS, and that happens quite often in this course. We have a stratified random sample, a cluster sample, Some forms of bias that we were exposed to were undercoverage, non-response, and different types of response biases. When conducting an experiment, we can have an observational study or an experiment. An observational study is simply observing something as it happens and recording the results. An experiment is being purposeful, purposely imposing some treatment onto your subjects. Right, we have treatments, experimental units, and subjects. Right, the treatments are the things we're imposing on our subjects. The experimental units is the smallest unit of people or things or objects that can receive a treatment. Sometimes that is the individual, sometimes that is a group of individuals. It depends. How to experiment? Well, we must have random assignment, comparison, control, and replication. Random assignment means that we randomly assign the treatments to the treatment groups. Comparison means we need something to compare to, right? We either need to have two different treatments we're comparing, a treatment in a control group. We need to have a comparison. Control is actually controlling other outside variables to make sure that you get a result that allows you to make an inference about the thing you were testing. Right? We must control things like, if we're giving a new medicine, what time of day everyone's receiving it, so they're getting it at the same time and they're getting the same doses. We want to make sure they're getting the same doses, right? They're on similar diets. We have people participating in the study who are of similar characteristics, things like that possibly. Those are all measures of control. Control in this sense does not mean a control group. We don't always need a control group. Lastly, we have replication, meaning we should have enough size in our study to actually get verifiable results. Completely randomized design. We want to always have completely randomized design if we can. We can need to be aware of placebo effect, double-blind, single-blind studies, and whether or not our results are statistically significant. We can also have block and randomized block designs, which a matched pairs design is a special type of randomized block design. Lastly, we have to consider our scope of inference based on the experiment or study that we've just done. What is the scope of inference? What population or portion of the population are we allowed to make a conclusion about? We have a little graphic here showing what a simple random sample, stratified sample, and cluster sample can look like in a nutshell. A simple random sample is taking a population and randomly selecting people from the population. The stratified sample is grouping people together based on common characteristics, and then randomly sampling from each strata. A cluster sample is when you group people together based on location. They're just simply close together, and then you randomly select clusters to participate in your study. If you use a cluster sample, the entire cluster participates in the study. The clusters that are not selected, no one from that cluster participates in the study. And there's a very common error when it comes to stratified versus cluster is to kind of misname them. Right, make sure you're using the one you're talking about. Our completely randomized design can be seen in this example here. We have a group of students. We randomly assign students to one of two treatment groups, and then we probably flip a coin to decide which group gets which treatment, treatment A or B. We compare our results. That is a completely randomized design. If we're using a randomized block design, we split the students up by academic year, freshmen and sophomores, we could say. And then we randomly assign the students within each group to one of the two test treatment groups, and then we flip a coin to see which group in each of those gets which treatment, and we compare the results of each of the blocks. All right, so this has an extra stage in it where we're grouping by a common characteristic, in this case, academic year. We could group by age groups, right, and that creates our blocks. Our specialized case of a block design is a matched pairs design, where we have the blocks, in this case of individual cars, which then get both treatments. We could also have pairs of individuals and then randomly assign one of two treatments to those pairs. Right? Each pair is a block. And we compare the results of each of those. Right? Those are special block designs. The matched pairs design results in one sample t-tests, as we saw in the end of chapter 9. All right, we go to chapter 1, exploring data. This is where we learn to make a little bit more sense out of data. We learn some vocabulary about what an individual is and what a variable is. All right. Variables are things that describe characteristics of individuals. Categorical variable, we have categorical variables and quantitative variables, and either of those can be described with a distribution. Right, a categorical variable is a category. Right? Hair color, eye color. Right? Those are categories. Those are things like I can't take the category of hair color, brown, blonde, you know, brunette, whatever. I don't know, those are all the same, whatever. But we can't take those and say, okay, I'm going to average those values because they're not values, they're categories. Quantitative variables are things that make sense to make an average out of, such as height, right, speed, velocity, things like that. Right. Categorical data, we use bar graphs and pie charts or two-way tables to display, and we can come up with marginal distributions and conditional distributions based on our categorical data, which allows us to make an association. Quantitative data is represented with dot plots, histograms, stem plots, back-to-back stem plots, split stem plots, and we'll always have shape, center, and spread and outliers when we describe them, or possible outliers, and we can use the acronym SOX or CUS to remember to do those 4 things. Quantitative data's distribution can be symmetric or skewed. A special case of a symmetric distribution is the normal distribution. Skewed distributions are described by the direction the tail is pointing. So a right skewed distribution has a tail to the right. A left skewed distribution has a tail to the left. Right? Our distribution can be unimodal, bimodal, or multimodal. Depends on our data. When we describe quantitative data, we want to make sure to describe the center, right, which can be mean or median, the spread, range, IQR, standard deviation, and identify any possible outliers. It is common to use the 1.5 times IQR rule to confirm whether something is an outlier. There are other rules that we could use, but in our circumstances, the one that's kind of easiest to do is the 1.5 times IQR. Box plots are created from the 5-number summary, a minimum, Q1, median, Q3, and a maximum. And we can stack box plots to be able to compare distributions, or we can simply compare histograms or dot plots or stem and leaf plots if we like. And we can compare them by comparing their center, shape, spread, and all those things. Here's an example of ways to display categorical data with a pie chart or a bar graph. There's a two-way table there that helps us describe categorical data. We have the categories on the top and on the left-hand side there, and then the count of each of those things occurring. And we also have our marginal distributions on the right-hand side and the bottom. When displaying quantitative data, we can use a box plot, histogram, stem and leaf plot, or a dot plot. There's little pictures of each of those here on the screen. One thing I do want to point out is the major difference between a histogram and a bar graph. A histogram is based on quantitative data, and the bars should be touching. The only time there will be a gap between bars is if there is no data in that particular bin. All right. Right, so if there was no data in this 11 to 15 range, it would be of height 0. There wouldn't be a bar there. Otherwise, bars need to touch on histograms. Where one bar ends, the next bar begins. With categorical data, when we're doing a bar graph, the bars do not touch. All right, they're completely separated. There should be space between them. In chapter 2, we went on to modeling distributions of data. We were describing location and distribution. We can describe location with percentiles. We can use a cumulative or relative frequency, a standardized score or z-score, and calculating a z-score is one form of transforming our data from our raw score to a standardized score. Density curves and normal distributions. Right? A density curve has an area of 1 under the curve. Right? The mean and median of a density curve are related. In a symmetric density curve, the mean and median are in the same place. Right? They're just right there in the middle. With a skewed distribution, with a skewed density curve, the mean will be pulled away from the median in the direction of the skew. Right? So if a distribution is skewed to the right, the mean will be to the right of the median. The normal distribution is a special example of a symmetric distribution. Special case, it is described with the notation n parentheses mu comma sigma, where mu is the mean and sigma is the standard deviation for that distribution. The mean and standard deviation completely describe the normal curve for any normal distribution, whether it has been standardized or is still in its raw scores. The 68, 95, 99, 7 rule, otherwise known as the empirical rule, can be seen in our normal distribution, saying there is 68% of our data within 1 standard deviation of the mean, 95% within 2, and 99.7% of the distribution or the area under the curve within 3 standard deviations of the mean. Standard normal distribution is what we typically use once we've standardized a score. We use that with table A, and that allows us to determine the proportion under the curve, or like p-values, so to say, as we've seen recently. And we can compare things of kind of like different scores on different tests that were done with different point ranges by standardizing each of those and comparing those z-scores. Right. Normal distribution calculations, all right? When we're performing normal distribution calculations, which we do quite often, we find the proportion of a curve based on a given value, or we can find a given value based on the proportion under the curve, or a percentile. When we assess normality, we should be looking for something that's approximately symmetric and bell-shaped and that is close to the 68, 95, 99, 7 rule, or we could use a probability plot on our calculator to see if we get a relatively straight line, showing that there is not much skewness. Here's a picture of that 68, 95, 99, 7 rule with a standard normal curve. And this is our basic z-score calculation, where x is the original score, mu is the mean, and sigma is the standard deviation. Different variants of this formula is what we've been using throughout the course. In chapter 5, we went into probability. We have randomness, probability, and simulation. Probability is always between 0 and 1 and describes a proportion of time a random outcome would occur in the long run. If you ever get a probability that is greater than 1 or a probability that is less than 0, you have made a mistake. That is not possible. You should never get a probability greater than 1 or less than 0. All right, if that happens, you have most likely made a mistake. Check your work. Simulations can allow us to model long-run behavior and imitate chance behaviors. We have some software that has done that for us throughout the semester, or we've just seen examples of how that goes. We have some special probability rules. All right, we have vocabulary, sample space. This is a set of all possible outcomes. All right, so let's, for example, consider the case where we're rolling 2 dice, a red dice and a green dice. All right, there are 36 possible combinations between these that these 2 dice can make when you roll them. Right, that makes up the sample space, all the possible outcomes, right, all the possible combinations. Probability model consists of a sample space and a probability for each outcome. Now suppose we say, okay, we've rolled these dice, we have 36 possible outcomes. I'm concerned about the sum of the 2 dice. We could then kind of convert that same sample space to show the sum of each of those dice. So rolling 2 ones has a sum of 2. A 1 and a 2 is 3, and so on, right? And we could then count the number of times each of the sums occurs and get a probability for each possible sum of the dice. That gives us our probability model. An event is any collection of outcomes from some chance process in a subset of the sample space. We could have event A be the having a sum on the dice that is equal to or less than 6. That's a possible event. If all outcomes in the sample space are equally likely, which is the case when we roll 2 dice and we get one of those 36 outcomes, they're equally likely because the dice are fair. The probability that event A occurs is the probability of A equaling the number of outcomes in event A. In other words, the number of combinations on the dice that result in a sum less than or equal to 6, divided by the total number of outcomes in the sample space, 36. Two events are mutually exclusive if they have no outcomes in common. For example, if event A is, as we've described, having a sum less than or equal to 6, and event B is having a sum greater than or equal to 10, those events are mutually exclusive. I cannot roll the dice and have both things happen. It's impossible for the sum of the dice to be less than or equal to 6 and at the same time be greater than or equal to 10. It isn't going to happen. Those are mutually exclusive or disjoint events. We then have a little bit more on the probability rules. We have our complement rule, which we actually use quite often in this course. That says the probability of A complement, that's that superscript C, is equal to 1 minus the probability of A. Again, if the event A is having the sum of the two dice being less than or equal to 6, then the complement of A, event A, would be the sum of the dice being greater than 6. Right, we use this complement idea when we're dealing with table A and we're asked to find the proportion under the curve where Z is greater than a value. Right, table A does not give us greater than portions, it only gives us less than or equal to portions under the curve or proportions. So we use the complement rule and say, well, we'll use 1 minus probability of Z being less than or equal to. We use the complement. Okay. Addition rule for mutually exclusive events. So this is when two events are disjoint. Probability of A union B, or the probability of A or B, is equal to the probability of A plus the probability of B. We use two-way tables and the general addition rule. When finding probabilities involving two events, a two-way table can display the sample space, making probability calculations easier. We saw an example of that earlier, or at least of a two-way table. Our general addition rule for two events, if A and B are any two events, meaning they could be disjoint or they could have an intersection, resulting from some chance process, then the probability of A union B, meaning A or B happening, meaning we could have one or the other happen and we're happy, equals probability of A plus the probability of B minus the probability of A and B. We subtract the intersection so that we don't count it twice. Venn diagrams can also help determine probabilities in modeling the sample space of a chance process involving two events. And again, a Venn diagram is like the two intersecting circles, so we can actually show the events that are, not in the intersection, the events in the intersection, and then other events that aren't part of either of those things within a sample space visually. We also have our conditional probability and independence. The notation P of B given A, right? That line, that up and down line there, says given, represents the probability that event B occurs given that A has occurred already. Notation probability of A given B is equal to the probability of A and B divided by the probability of B. Right? Determine the denominator here. The probability of B is whatever term is the given event. So this is the probability of A given B. Since B is given, that one goes in the denominator in this calculation. And the screen's always lagging. There it is. We have our general multiplication rule, the probability of A and B. Right? So the probability of A and B occurring at the same time is the probability of A times the probability of B given A. Okay. We can also kind of rearrange this and say it's probability of A and B is equal to the probability of B times the probability of A given B, depending on which information we have. Right? When chance behavior involves a sequence of outcomes, a tree diagram can be used to describe the sample space. And again, our tree diagram is when we have kind of like a series of events or choices that occur, and each time one of these things happen, we get a different set of branches for the possible outcomes again. Right? And we can use this to kind of follow some logic through and calculate a probability essentially just by multiplying the probabilities through the tree. When knowing that one event occurred does not change the probability that another event occurs, we say the two events are independent. Right? Probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B if events A and B are independent. Right? We use the idea of independence a lot throughout the rest of the course. If two events are mutually exclusive, meaning they are disjoint, they cannot be independent. If we think back to the previous example with the rolling of the 2 dice, if I know that the sum of the 2 dice is greater than 10, then I know the probability of having the sum of those 2 dice being less than or equal to 6 is 0. That means knowing that that one event happened has changed the probability of another event occurring. That is why when two events are mutually exclusive, they cannot be independent. If events A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. Then we get into the beginning of second semester with chapter 6 on random variables. We dealt with discrete and continuous random variables. A random variable takes numerical values determined by the outcome of a chance process. The probability distribution of a random variable x tells the possible values of x and the chances that each of these values occur. Again, this is essentially the same idea as on the previous one with chapter 5. If I roll 2 dice, the random variable x could represent the possible sum of the 2 dice. The possible values for x is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The probability of having the sum be 2 is 1 out of 36. Probability of the sum being 3 is 2 out of 36, right? And so we can fill in a table that shows each possible outcome or value of x and the probability of that value occurring. Discrete random variables have a fixed set of possible outcomes, such as the example I just said. Continuous random variables take all the values in some interval of numbers. An example would be if x could take on any value between 0 and 1. There is an infinite number of values because for each value you give me, I can add something to it to get another value. Right? That is still less than my endpoint. Right? And that's why it's continuous. There's no gaps. If x is a random variable, then the mean or expected value is the average of the values of x. Right? The mean of x is equal to the expected value of x, which is equal to the sum of each possible outcome times the probability of that outcome. Right? The variance of a random variable x, right, is sigma squared x is equal to the sum of the difference between each observed outcome minus the mean. That should be mu x squared times the probability of that outcome. We add all these bad boys up. That's the variance. We take the square root of that and we have the standard deviation. Your calculator can do these things for you, especially if it gets beyond more than like 4 or 5 observations. You really don't want to do this by hand. It can get tedious. We can transform and combine random variables, and we use this idea when we get to chapter 10. We can add or subtract a constant to a random variable, which will increase or decrease measures of center and location. For example, mean, median, and percentiles. Adding a constant does not affect shape or spread, as it is subtracting a constant. We can multiply or divide a random variable by a constant, and that multiplies or divides the measures of center, location, and spread. Right, so in addition to affecting the mean, median, and percentiles, we also will change the IQR, range, and standard deviation. Again, neither of these things will affect the shape. If x and y are any two random variables, then the mean of the sum of the two random variables, x plus y, is equal to the mean of x plus the mean of y, and the mean of the difference of the two random variables is equal to the mean of x minus the mean of y. We use this in chapter 10. If x and y are independent random variables, then the variance of the sum of the two random variables is the variance of x plus variance of y. Also, the difference Right? The variance of the difference of the two random variables is equal to the sum of the variances of the two random variables. We can also have binomial and geometric random variables, right? If we're doing a binomial random variable, we must check that we have a binomial setting, meaning you've got to check your bins. Is it binary? Are we either successful or fail? Is it independent? Does knowing one event's outcome affect the next one? Does one trial change the probability of success in the next trial? Number. There needs to be a fixed number of trials in this setting, and the probability of success must be the same for each trial or each thing that's happening. If X has a binomial distribution, meaning we've checked our bins and it is all good, with parameters N and P, N is the number of trials and P is the probability of success in each trial, the possible values of X are the whole numbers 0, 1, 2, all the way up through N. We can only have as many successes as we have trials. The binomial probability of observing K successes in N trials is the probability of X equaling K, which is equal to N choose K, that is not division. Those numbers are, those variables are just stacked on top of each other. N choose K. Your calculator can do this. It's saying how many different ways can I have K outcomes, okay, successes in N trials, right? Times probability of success to the power of the number of successes times the probability of failure, 1 minus P, to the power of the number of failures, N minus K. The mean and standard deviation of a binomial random variable X are mu sub X equaling NP and sigma sub X equaling square root of NP times 1 minus P. A geometric setting is when we have repeated trials of the same chance process in which the probability P of success is the same in each trial, similar to our binomial setting. However, the goal is now to count the number of trials it takes to get one success. So we will always just have one success. We're just trying to figure out how long it gets there and how long it takes to get there. If Y has a geometric distribution with probability of success P, possible values of Y are the positive integers 1, 2, 3, up to infinity. The geometric probability that Y takes any value is P. Probability of Y equaling K equals probability of failure times, or not times, to the power of the number of failures, K minus 1, times the probability of success. The mean of a geometric random variable is mu sub Y equaling 1 divided by P. That brings us to chapter 7. How much time we got? 10 minutes, okay. All right, chapter 7 was our sampling distributions. Right, the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the population. Our sampling distribution of a sample proportion is as follows. We choose an SRS, a simple random sample of size n from a population of size n, capital N, with proportion P of success. We will let P hat be the sample proportion of successes. Then the mean of the sampling distribution of the sample proportions is equal to P, and the standard deviation of the sampling distribution of the sample proportions is equal to the square root of P times 1 minus P divided by N. Right? This square root thing here turns into our standard error in chapters 8 and 9. These results are only valid if the 10% large counts conditions are met. Right? The 10% condition allows us to confirm that our standard deviation is viable, and the large counts condition is our assessment of normality, and we need that. We can also do the sampling distribution of a sample mean, where we suppose that X bar is the mean of an SRS of size n drawn from a large population with mean mu and standard deviation sigma. Then the mean of the sampling distribution of the sample mean is equal to mu, and the standard deviation of the sampling distribution of the sample mean is equal to the standard deviation divided by the square root of the sample size. And again, the standard deviation is valid if the 10% condition is met, and we can only use normal distribution calculations if the normal large sample conditions are met. The normal large sample condition is that either the parent population is normal, in which case the sampling distribution will have a normal distribution, or the sample size is sufficiently large, meaning it is at least 30. Otherwise, we need to check the distribution for normality, meaning we have to get our data points, look at the graph. Is it strongly skewed? Are there any outliers? If the answer to either of those questions is yes, then we cannot move forward. We cannot use normal distribution calculations. That gets us to Chapter 8, confidence intervals. When we're interpreting confidence intervals and confidence levels, right? To interpret a C% confidence interval for an unknown parameter, we say we are C% confident that the interval from blank to blank captures the parameter in context. That depends on whatever the context of the question was. To say we are C% confident is shorthand for if we take many samples of the same size from this population, about C% of them will result in an interval that captures the actual parameter value. When calculating a confidence interval, the confidence interval for estimating a population parameter that could be proportion or mean has the form statistic plus or minus critical value times the standard deviation of the statistic. The margin of error is the critical value times the standard deviation of the statistic. When we're estimating a population proportion, we must check our conditions before constructing a confidence interval. That is, the random, 10% when sampling without replacement, and large counts conditions are met. Then we use the one sample z interval for population proportion inference method. That is p hat plus or minus z star times the standard error, which is the square root of p hat times 1 minus p hat divided by n. Where z star is the critical value for the standard normal curve with C% of its area between negative z star and z star. Again, we find a z star based on the confidence percentage, the C%. And table A. We got to use table A on this one. Constructing confidence intervals, always use the 4-step process: state, plan, do, conclude. If you're not doing this right now, then and you are taking the AP exam, you're not going to get full credit for your responses. That's just kind of the bottom line. If you're not doing these things, if all you're doing is showing calculations, chances are you're not going to pass. All right, you have to show these things. This state, plan, do, conclude process is there for a reason. It's to ensure that you cover all the things you're supposed to do to get credit for your response. To determine the necessary sample size for a given C% confidence interval with a maximum margin of error, ME, solve the following inequality for n. Right, so based on that C% confidence interval, we can calculate the z star and put that in the formula. The p hat is based on whatever our sample was. So we can get p hat and 1 minus p hat divided by n, and we don't know. We are solving for n is less than or equal to the maximum margin of error. If we're dealing with proportions, that will be a percentage, which we will convert to a decimal to do our calculation. Estimating a population mean. Before constructing a confidence interval for estimating a population mean, you must check that the random, 10% sampling without replacement, and normal large sample conditions are all met. Then you use the one sample t interval for a population mean inference method. Right, and this is x bar plus or minus t star times the standard deviation of the sample divided by the square root of n. Right, where t star is the critical value for the t to t sub n minus 1 distribution, right? That is our degree of freedom, one less than whatever the sample size was, on table B, with C% of its area between negative t star and t star. And again, you find this t star value based on the degrees of freedom using table B. Again, please use your 4-step process. To determine the necessary sample size for a given C% confidence interval with a maximum margin of error, ME, solve the following inequality for n. Even though this is dealing with sample means, we will use the z star value for this calculation, meaning we will go back to table A and find the critical value z star based on the confidence interval we're looking for. We will have an estimate for sigma based on either our sample or some previous results that we will use as our best guess, and then we'll solve for n. In this case, the margin of error should be a number, depending on your context. If the acceptable margin of error for your average, for your mean, is 2, then the margin of error is 2. You do not need to change that to a decimal. It's just a number. And we're going to stop here. Obviously, we did not finish everything. However, we've only got like 4 minutes left in class. And your next class starts at 1:35. I want to make sure you have enough time to get to that. So we're going to stop here. All right. So again, obviously we didn't get through all of that. We got through a good chunk. There's still things on that for Chapter 9 and Chapter 10. I encourage you to look through this if you would like to. Also, in Canvas, I have linked some videos that have been produced by College Board and AP and everything for reviewing specific topics that will be covered on the AP exam. Those are at the top of my modules pages. It is a module, it's videos. The videos are about 45 minutes piece, though, just so you know. Those are longer videos. All right. If there's any questions, comments, or concerns, please feel free to stick around and ask. We have a few minutes before the next class. Otherwise, I will see you all tomorrow, where we will do some AP exam practice stuff. Have a great rest of your day.